All right. So for today's lecture, we are going to discuss basically the last two relevant items in the theory of Markov decision processes and how to optimize decision making. And so in the first half, we will basically discuss how to put at work all the theoretical results that we obtained in the last couple of lectures. That is how to construct algorithms to search for optimal strategies in policy space. And that would be that for the first half. And in the second half, we will address the problem of what can we do when the state space or the action space is just too large. Okay, so we cannot approach such a search procedure or directly the optimization via the solution of the Bellman's equation, just because the sheer size of the state action space is so huge that we cannot address it, and therefore we will discuss how to combine these algorithms with the function approximation. Okay, so that's the plan for today, but let's go one step at a time. So let me start by giving you a brief recap of what we have in our hands so far. So on one side, we have the solution of the Bellman's equation. Fine, we will use it explicitly tomorrow in the tutorial. So in the lecture tomorrow, we will see how to explicitly solve the Bellman's equation in two examples. One is the traveling salesman problem, in which the problem is explicitly time dependent. And then the second one will be solving the grid world in one or two instantiations, again by Bellman's iteration, that is by the value iteration algorithm. But now we are focusing on algorithms that take explicitly into account the policy, the structure of the policy. So summarizing our results so far, we have been somewhat painfully, but successfully been able to derive the following expression. So remember, just recall that our goal, as always, is to find the policy which maximizes our total gain, which is more explicitly find the policy which maximizes the expected value of the sum of discounted rewards along a trajectory generated by our Markov decision process. And yes, what you have shown yesterday is that we can explicitly write the gradient with respect to any component of a policy, pi, in the following form. These eta and q are two functions, respectively a vector and a matrix, that have a very specific interpretation in terms of basically these are the can be interpreted as occupation times of state S discounted, and this is the state action value function. Okay, so let me just recall you the basic definitions of these objects. So the eta as a vector was defined as 1 minus gamma p to the minus 1 times rho naught. So this rho naught is the initial distribution over states. Okay, this is where my system is at the initial time. It could be localized on one state, it could be dispersed across all states. And this capital P here is a matrix whose entries are defined to be just as the transition probability from one state to the next one, given the policy pi. Okay, so this P implicitly depends on pi. Sorry, explicitly depends on pi, and pi implicitly, and eta implicitly depends on pi through the dependence on P. Okay, and then what is Q? Well, Q is defined as the expected value under the policy pi if we start from a certain action state S and we pick action A, which means that if we are in state S and pick action A, we will end up in state S prime, and in this process we will incur a reward SA S prime, and then from state S prime, what we will get under that policy is the value starting from state S prime. And what is the value? Well, the value, you can also rewrite it in a simple form, just as the following definition. This is just RT 1 minus gamma capital P to the minus 1. This is the same capital P that is above. And what is this? R is a vector, is a row vector whose entries are just the expected rewards starting from state S. So if I'm in state S, I take action A according to my policy. I end up in state S prime according to my transition probability. And then I collect an average reward, or SA S prime. Okay, so far so good. This is just a very short summary of definition. So in practice, okay, so let's go back to our example when there are two states and two actions. Two states, two actions. In this case, the policy space is a square. Okay. So on this axis, we have the probability of taking action 1 given state 1, and here we have the probability of taking action 1 given state 2. Okay, these are the only independent variables in terms of the policy, and my G is something that looks like something like this. Okay, this is the level lines of my G function. And then the gradient is some vector. So if I take any policy pi here in the middle, okay, this is my gradient of G. Okay, so and this point here is any policy pi for my system. So how does that work? How do I compute this gradient in practice? Remember, we start with some things that we know. Okay, so the known things are the initial density, the initial distribution over states, the policy, okay, which is something we choose at any given point in this space of policies. Then we know the transition probability is small p, and we know the rewards R. Okay, these are parts of the model that we have and we assume to be correct. Okay, and then from this we can construct several things. So from pi and p, okay, look at this formula here. Combining a linear combination of pi and p gives me capital P, and a linear combination of pi, p, and r, okay, differently arranged, So I can combine these three together, P, pi, and R, to get my capital R. And then if I combine rho naught with capital P, I can get eta. Okay, so how do I get this in practice? Well, one possibility is that now that I have my capital P matrix, I could just make this linear combination and then take the inverse. The inverse is relatively expensive as a procedure, so if your matrix is large enough, you might resort to other techniques from linear algebra, okay? Whatever. The important thing is that this is a linear object. There's nothing nonlinear happening here. You just have to do inverses, or you can use iteration methods. So you can deploy all the linear algebra that you know, just take off the shelf any solver for a linear equation, and that will do. I mean, the fact that this is a linear equation, you just realized because this is equivalent to 1 minus gamma p times eta equals rho, okay? So you know this can be written as a linear equation of the form matrix capital A times eta equals some rho naught. Okay, so you just have to solve a linear problem here. And same for V, okay? V is also the solution of a linear problem, which is nothing but the recursion relation, in the sense that V transpose 1 minus gamma p is equal to R transpose. Again, same structure, only that now you're multiplying on the left. Okay, so this is your unknown, and this is the matrix, this matrix you know, and this column row of entries you know. So it's just an inversion, and you know that these matrix that you have to invert is well behaved. So okay. And then this means that if I combine P and R, I can get my value function. And then from the value function, I obtain, by combining it with the small r and p, I get my Q. Okay, so these things are already in stock. This object here is also known. So the three of them together give me the Q. And eta and Q together give me my dg in d pi. Okay, so this is the flow of operation that you have to do. If I give you a policy, you will be able to compute the gradient, given all the other side information which are important. That is, what is the initial distribution of states, what is the transition probability small p, and what is the reward structure small r. Okay, and all of this is just linear computation, so you can figure out what the complexity of these operations is, and as you can clearly imagine, this complexity grows very, very rapidly with the size of the system that you're considering. Okay, but conceptually speaking, there's no mystery, no difficult step here today. So now that we have our gradient, the question is, what can we do with that? Okay, in this case, in this specific case, we know that the optimal solution is here. Okay, just because I draw it like that. If you try out a different combination of rewards and transition probabilities for your two states to action model, you might find different landscapes of your G function. Okay, so let me repeat again. These are the level lines of G. Okay. So G here is increasing. And here is the maximum. So this one would be my optimal policy pi star, which according to this sketch would be, this would mean every time that you are in state 1, pick action 1. And every time that you are in state 2, pick action 2, because the probability of picking action 1 is 0 here in this point. Okay. So the question is, how do we get from any initial policy pi to our optimal policy? So how do we search for this maximum of G in policy space? So in practice, what we are looking for is some sort of gradient ascent. Okay, we want to climb the gradient until we get to the maximum, which we know it sits on the boundary. So what we're going to do now in this next 20 or 30 minutes is to study different approaches to this problem of optimization when you know a gradient. So the things that I will describe now are in part are common to all kinds of optimization problems, and in part are specific of this optimization problem of an MDP. Okay, so some things will be general, some others will be more specific of this problem, but these are nevertheless very, very broad concepts and ideas. Okay. Fine. So the first algorithm that we will discuss goes under the name of policy iteration. So what is the idea? Well, the idea is very simple. It's sort of brutal in the sense that I rewrite here that my gradient is this object here. Okay. So once more, I hand you a policy, and then you can compute all these components of the gradients. For every pair A and S, you have a real number, which is the right-hand side here. And this tells you basically how much your objective function depends on the various components of the policy. So policy iteration does the following thing: suggests to pick as an action the one which maximizes the component of the gradient. So let's go back to our sketch here. So you have components for each direction. Okay, so you have your component in this direction of the gradient, you have your component in this direction. And then for each of those, you pick the action which gives you the best. And so in this case, for instance, this gradient is telling you, you should move to the right and you should move down. Okay. So what this policy iteration is doing is basically telling you, believe in your current gradient. Wherever you are, choose your gradient and go all the way to maximize within your policy space in that direction. Okay. So you just compute the gradient and you go full throttle in that direction, which is what is expressed analytically by this expression here. Okay. So among the many components of your gradient, you pick the largest one. Okay. So just to give you a further example. So suppose that now you're somewhere and you're told that you have to go, say, for instance, in direction north-northwest. Okay, so you have a compass and you say, okay, I have to go north-northwest. And what you're going to do with this is that you're going to go north, because north is the direction which is closest to your orientation of the gradient north-northwest. Okay, so basically you ignore all the variations, you just fix on your relevant axes, which are just north, south, east, west. And we say, okay, I'm going to take the direction which has the largest component of my gradient. I hope this makes the idea clearer and not more confusing, but if you're not totally clear with this, just let me know. So by definition of the gradient, okay, if I have to pick the maximum over my A's, This means that this eta does not play any role here. And this is just the argmax over A of my QSA. So this choice is also called the greedy optimization. Okay, it's greedy because we just based on our current knowledge of what we're gonna get in the future, according to this strategy, we go all the way with it. Okay, so we do not allow for any other possibility than this being true. Okay, so in graphically speaking, if we go to our example, okay, again with two states, two actions. This is my policy space, the graphical representation. So now suppose that I have a different form of my Q function, of my G function over that, okay? So that, for instance, locally, my optimum is here, but locally my gradient points in this direction, okay? So it might well be, right? That is, it has some form like this. Okay, so that eventually your maximum is here, but if you start from some point here, maybe your gradient is pointing in that direction. So if you apply this algorithm, this will send you, as a first step, will send you here. Okay. This is what this is telling you. Pick a policy, your new policy, pi prime. If you follow the gradient like this, will be a deterministic policy which assigns with probability 1 the action A tilde and with probability 0 any other action. Okay, remember, this is the characteristic function of this condition, so it means explicitly that this object is equal to 1 if A is equal to A star of S and 0 otherwise. Okay. So if I do this, then my local gradient here will tell me, okay, you have to go here. So my pi prime will be here. And then if I repeat, what I'm going to do is now I'm going to evaluate my gradient in this new point here. Okay, so my new gradient will be pointing like this. So, and if I follow that and I repeat my operation, where will I go? I will hop here. Okay, so this is at my time, my second guess now will be here. And if I compute the gradient here, now my third guess will send me, the gradient will send me here. And if I follow the gradient, I will end up here, which eventually will be my maximum. Okay, so in this sketch, starting from a point pi, I have made 3 steps to get the maximum. Because this operation of picking this greedy optimization sends me straight in the corners of my policy space. Remember, in general, the policy space is not a square, okay? It's a more complicated object, but it has corners, and these corners correspond to the deterministic policies. All those that are made of a single one for one action and all zeros. So this idea of policy iteration in a nutshell is compute the gradient, then go to the corner where your largest component of the gradient sends you, and then recompute the gradient from that corner, go to the corner which in which you are directed to, and so on and so forth. So there are two questions here, of course, that arise. First of all, is this ever going to converge? I'm hoping through corners. So in general, my state space, suppose that I have S states and two actions. My policy state, my policy space is an hypercube, okay? So policies belong to 0, 1, okay? Because if I have just two actions, there's just one single real variable from 0 to 1, which describes the policy. So here is, for instance, probability of taking action 1 in state S. And so this is power to the S. So this is an hypercube, an S-dimensional hypercube. So my algorithm, my policy improvement algorithm, as it is defined, would start somewhere in the middle of this cube, then jump to one corner, then jump to another, but there are exponentially many of them. Okay. So will it converge eventually to the optimum? First question. Second, isn't it stupid to generically look around for something in the corners that could take a long time to explore, could be exponentially long time to explore. Okay, so first we address the first question. Okay, let's see. Now we're going to prove that this policy improvement algorithm does indeed converge to the optimal solution, which makes it sensible as an opportunity. And then in the second step, we will address this question: can we do something smarter than this? Everything clear so far? Any question? Okay. So let me, this was a very sort of informal description, but now we can describe the algorithm in full. So this algorithm, which is called policy iteration. So the pseudocode for this is initialize a certain pi 0. Okay, this index 0 is just a counting index, which tells me what iteration I am in. Okay, so this is the first initial step. I choose one policy, whatever, any admissible policy, anything that is inside my space of policies. Then I have a loop that goes as follows. From any pi k, okay, I obtain a value function. Okay. How do I do that? Well, let's go up a bit. You remember this flow here. So if I have a policy, I can construct all these terms and I can get my value function. So this step of given a policy, computing the value function is what is called a policy evaluation. Okay, it's pretty self-explanatory as a term. You have a policy and you compute a value function. Now, from this value function, you can compute the corresponding Q, okay, which is defined, you remember here. So from this line, you have a value, all these things you knew from the beginning, so you can combine them together and get your Q. And then from your Q, you get, through the greedy choice, you get a new policy pi k plus 1. What does this arrow mean? Well, in practice, this means that your pi k plus 1 AS is just the arg max over actions a bar of Q K S a bar. Okay, so this is what I just wrote above here, exactly this notion. So it's your A tildes are here. This is also equal to 1 over A tilde K, because this is taken from QK of S. So you see the flow. Policy, value, value, Q function by the greedy choice, new policy. Then K plus 1 goes into K, and you close the loop until some termination condition. For instance, usual request is that your value function isn't changing much, is less than some epsilon, which you decide beforehand. Or again, you might choose the relative change in V. Okay. So this is the algorithm. And what we're going to do now in a few lines is to prove that policy iteration converges to the solution of the Bellman equation. Okay, so this is not very complicated. So we're going to do this in a second. So the key step is to show that when we perform one step of this loop, we go from one GK to a new GK plus 1. Okay, so this G is my objective function. So this means that in my graph, every time that I make a jump like this, I'm actually going to a level lines which is higher. So what we're going to show is that this object here is larger or equal than the previous one. So there is an ordering here. Actually, the proof goes into two steps. The first step will be that it's always larger or equal to the previous one, the value of my objective function under one iteration of the policy. And the second thing will be that if it's equal, then it's the Bellman's equation, and this will close the matter. Okay. So by the way, this second step here, so this first step is policy evaluation. This second step is called policy improvement. So this policy iteration algorithm is an alternation of two steps. Start with a policy, evaluate it, which means compute the value function. Then from the value function, through the greedy assignment, compute a new policy. Repeat. Okay. So the proof goes as follows. So remember that for any given policy, my objective function is can be written in terms of the value function as the distribution of initial states times the values from those states. This is just another way of writing the expectation of sum over 0 to infinity of gamma t. All right. Now let's concentrate on the value function. So the value function for my policy pi is just very simply connected to my Q function. Okay, so this first step is quite straightforward. Let's go up a little bit to the definition. So sorry. okay? So this object here is the definition of Q. And if you sum over the policy on both sides and perform the summation, you realize that you find back again your iteration formula here. Okay, so this is the connection between the value and the function, or more directly. So what is the value function from state S? Is what you expect to gain starting from that point, according to the policy pi, which in itself is nothing but pick action A, and then this will be what you expect starting from that pair state action. Okay, so quite straightforward. All right. Now we're going to use the definition of my A tilde here. So what is A tilde? Is the maximum overall possible actions for my Q. So by definition, each of those is smaller or equal than Q pi S A tilde of S. This is by definition of A tilde. Because for any S, for any row S of my Q matrix, I pick the column which has the largest Q. Okay, so this is the first step. And the second step is to use the definition of Q pi. By definition of Q, this is equal, sorry, just one step before. So this object here, now notice, sorry, one more step before we go there. So we take all possible precautions. So now notice that this term here does not depend on A. So this means that our sum over A is only restricted to the pi's, which are probabilities, and therefore this object is equal to 1. So my sum reduces just to A tilde of S. And then I can use the definition of Q pi, which is just sum over new states, P S prime S A, and then I have where here I have, instead of these A's in general, they are present in general, I have my A tilde of S. Okay, so what this means that at my current state, I'm picking the greedy action, A tilde, and then from that point on, I'm still sticking to my policy pi. All right. Now, look at what we have here. We have our policy, and we have the same policy in a new point S prime. And these are linked by an inequality. So what we're going to do here is just we're going to plug back this inequality back here. So this object here will be smaller than something on this side. Okay, so I'm going to apply again this inequality iteratively. B pi of S prime is going to be smaller than some other thing. Okay, so let me write it explicitly. Iterate the inequality. And then I get that this is smaller or equal than, I have my first part here, sum of S prime, P of S prime, S A tilde of S R S prime plus gamma. And now this object is smaller than, again, the right-hand side. So I have another sum inside here. Now with respect to S second, P of S second, S prime, A tilde of S prime, times R of S prime, okay? And then I could do this again and again and again. So I can unroll all these inequalities. And what do I get? Well, look at each of these terms. So the first term here, which comes from this contribution, well, this is the expected reward under the choice of the greedy action. Okay. And the second term is gamma times the reward that I will get at the next step if I still keep on using the greedy action. So just with a moment of reflection, you realize that this object here is nothing but the expectation of the sum from t going to 0 to infinity of gamma t of the reward that you take if you are in state st. You pick the action A tilde of st and you end up in state st plus 1. This conditioned on S0 equals S. Just by repeating this unrolling of this inequality, eventually this will be less equal than the sum of everything. But this object here is the G taken according to the greedy policy. So this is G of pi prime. By definition, because I'm taking, every time I'm picking A tilde, which is my choice according to the pi, to the iteration pi prime. So if you look at this, sorry, this is not G pi, my bad, I'm rushing this through. This is V pi prime of S. So if you look at the term, the final term here and the initial term here, these are connected by a series of inequalities which go all in the same direction. So I can conclude that the value function of the new policy is larger than the value function of the previous policy during one of these steps of policy iteration. And this, of course, implies, if I sum by the, if I average over the initial distribution, this implies that my G pi is smaller or equal than G pi prime. So this confirms the not so obvious intuition, actually, that every time that you make a step according to this greedy strategy, which sends you in the corners, you're actually improving your G. You're moving up in the level lines every step. Okay, final conclusion about this. What happens if there is an equality? Okay, if G pi prime is equal to G, then what do we have? Well, we have that. This means that V pi prime of S is equal to V pi of S. But let's go one step at a time. So V pi prime, by definition, is the maximum over A of Q pi SA. Okay, so this is the greedy choice. But since pi is equal to pi prime, this is also equal to the maximum over A of Q pi prime SA. Okay. But this in turn is equal to max A by definition of sum over S prime again using the definition of Q. And now if you look at this object here, this equal to this is just the Bellman's equation. So this is, I mean, this is a sort of lengthy manipulation, nothing particularly interesting here, apart from the bottom line, which is that this process of using the gradient to visit all the corners of the policy space in order is guaranteed you to bring from one corner to a better corner and eventually reach, without exception, the optimal policy. So this motivates the use of this policy iteration approach, which you will find described also in the book by Sutton and Barto, but without making reference to gradients, okay? But you have to realize that that's exactly the same thing that we're discussing here. Okay, so is this a smart idea after all? Well, there might be something smarter, right? So if you have a gradient, you might want to look for instance, gradient ascent. So rather than jumping on the corners, you might want to look for some way to go down the gradient, which will take you some sort of a trajectory like this. Sorry, going up the gradient, because this is a maximization process. So how do we do gradient ascent for this problem? And that's what we're going to do after the break, okay?
Sorry, can I make a question?
Yes, please.
Is a question about the notation. I didn't understand the difference between A tilde and the PK+1, because in the policy improvement, we are using the formula of the A tilde. And then for saying that PK+1.
You're making reference to this
yes,
one?
Yes.
Yeah.
Because up we wrote that A tilde is equal to this formula.
Yes, that's exactly the same thing. So there's no difference except that you are repeating this operation at every step, which means that you have a different Q over which to optimize. So if you give me something more, I can explain more, but I'm not sure I understand the
No, it's because no, okay, got it.
Is it clear, or you're just giving up?
Oh no, okay, I have to watch it maybe better later, so no problem.
Yeah, we can go through it. I mean, if it's I think it's helpful for everyone. So this choice corresponds to picking up the column in the Q matrix which has the largest entry. So given a row labeled by a state, for each row we pick up the column which corresponds to an action which has the largest entry, and this defines our A tilde of S. Okay, so in our Q matrix, which for instance is made of states and actions, So for every state, we run through the values of this Q, and then we identify the one which has the largest entry. Okay, so for every row, this dot means the ones which has the largest entry, which may be equal or different. And this defines my A tilde of S, because for every S, I have an A tilde of S. And I can do that for, so given a policy, I compute a Q. Okay, so given a policy pi, I can compute a Q. And from this Q, I can compute my alpha tilde. Okay, so this is the first step, which is called the greedy operation here. And I'm repeating this thing over different policies. So I take one, and then I use this new policy to compute a new Q function, which will give me a new policy by the greedy choice, and so on and so forth. Is that any clearer?
Yeah, thank you.
Thank you. Any other question? Okay, then we take a break until 10 past 10, and then we resume with the rest. All right, I'm going to share my screen. Okay. So we've seen that there is one possible way of exploiting the knowledge of the gradient of our objective function in policy space, and it is through this policy iteration algorithm, which basically sends the policy in the corners of our policy space, and then jumps from one corner to the other according to the direction of the local gradient. And this is guaranteed to terminate the search in the corner which has the largest value of our objective function, which corresponds to the choice of the solution of the Bellman's equation. Okay, but like we said, there are other ways of using the gradient, and perhaps the most intuitive and natural one is to use it in a more local way, rather than jumping around in the policy space, to follow locally the gradient and to climb the landscape of the objective function, which is depicted in this picture by this green path, which is described here. So, so the basic idea is to move to different kind of algorithms, like inspired by gradient ascent. So how does, intuitively, how does gradient ascent work? Well, the idea is that if you have a gradient, you could say, okay, I'm going to move from my current policy using some little step beta in the direction of the gradient. Okay, this is a very intuitive idea. It's making us a step, and the length of this step in the general case is proportional to the intensity of the gradient, and this called proportionality constant is called the step size beta here. And of course, there are immediately, and this is very general as approach, so it's it could be policies, but it could be any space, any domain, any function, any real function on any domain. Of course, the question is, how do I choose the step size? First thing, and the second thing is, what should I do if I end up outside of my domain? Okay, so let's address the second question first. So again, using as an example of policy space my square. So if I am at a certain point, I suppose I'm considering policy pi here, and my gradient is pointing in this direction, then clearly, if my beta is large enough, or if my pi is close enough to the boundary, I may end up with my new point pi prime, which is sitting outside of the domain. So what should I do in this case? Well, what all these kind of algorithms do is to prescribe some way to remap the point again inside the domain or on the boundary of it. So all these kinds of procedure like gradient ascent are usually combined with some projection back in the space of policies. So it's almost always necessary to do that, except in some cases. There are some cases in which if you do the gradient smart enough, well, you can happen to stay always inside the domain, and we will see an example later on. Okay, of course, here there is an issue, if you want, that is that the length of the step that you're doing in this process depends on the strength of the gradient, if you keep a beta constant. So another opportunity that we have is to use a constant variation. So what is the idea? The idea is, for instance, you could do, okay, let's use the gradient, but now we use it in a different way. That is, we normalize the gradient by its length. So what is it, the advantage of doing that? Well, is that now your parameter beta, you can interpret it as the distance between the previous and the second. The previous and the following policy. Okay, so in one case, if we go back to this scheme here, so in this first case, let's say that this is the one in yellow. No, I'm not managing to. Okay, that's not painful. So let's say this one. So what this algorithm is doing is that if it starts from a policy, then there is some gradient which is pointing like this from here, and then it makes a step to a new policy pi prime, and then in this new point there is a gradient which is, for instance, much longer, much larger in magnitude, and then this new point will be pi second. So the distance in policy space depends on how large the gradient is. This is the first option. What this other algorithm would do, let's think one. So what this algorithm does is that it moves along the same directions. So it always starts from pi. And then it goes by the same length, always the same length, okay? So all steps are the same or of the same length. So it moves more uniformly in the space of policies, which is also a reasonable option, okay? One can perform a lot of analysis on these algorithms and prove that they converge, at which rate that they converge, what are the properties that must be enforced, typically convexity of G, but this is just an overview to let you realize that there are actually many options on the table once you have a gradient at hand. Okay, and this requires also a lot of craftsmanship in choosing the proper ways to do it, depending on the problem and depending on the space that you.
I have a question.
Yeah, please.
So how do we exactly know that we are outside the space of policy?
Well, you at every step you have to do the check. Let's go here.
So the boundary of the policy, the boundary of space policy aren't known for us.
The boundary, sorry, is
the boundary of this policy space.
Yes.
We don't know them.
No, well, you actually know, because the check that you have to do at every step. So check if all the pi must be non-negative, and the sum for every s, the sum of pi a s must be equal to 1. So you realize immediately if you're violating these conditions, and in which case you have to do some kind of projection. Okay, I'm not spending a lot of time about what kind of projection you can do, but there are several, and it's a piece of analysis in itself to properly define projections, because if you define them in the wrong way, maybe you get stuck into some bad place in your domain. There's a good way of doing it that preserves the. But I'm not spending time on this because actually we've never used this.
Okay, thank you.
Okay, so one thing that you should quite immediately realize is that when we reason in terms of the length of the steps that we make, the distance between one policy and another, we are using the Euclidean distances here. But does it make sense? Does it make sense to define the distance between two probability distributions in terms of Euclidean distance? It's legitimate, but maybe there's something better that we can do here, something more meaningful. Okay, so in order to understand what we can do, let's reconsider the gradient ascent from a different viewpoint, slightly different viewpoint. So you might have seen this before. So this is called gradient ascent. Revisit. So what I'm going to tell you is that you can see one step of gradient ascent as an optimization problem of the following sort. So suppose you want to take the maximum over all pi's. I'll write and then I explain what this means. Of gradient of g times pi prime minus pi. This is computed in pi. Minus, there's a beta, minus 1/2 of the Euclidean norm squared. This is the L2 norm. So what am I writing here? So suppose that I have a policy pi. Okay. I have a gradient, grad g in pi. Then this quantity here is approximately, is a first order expansion. So it's approximately equal to g pi prime minus g pi. Okay. It's a local Taylor expansion of the difference between my value in the new point pi prime and in the previous point pi. Okay, are you clear with that? Just first order expansion of g pi prime around pi. So this term here inside the bracket means that we are trying to get the largest possible value of g but we are adding some cost for being too far. So we are trying to compromise between following the gradient in order to optimize over my objective function, which is the first part here, and the cost for going too far. And the parameter which trades off these two requirements is my beta here. Okay, is it clear? So if beta is equal to 0, then I don't move. Pi prime will be equal to pi, because clearly the maximum of minus the distance squared is equal to the minus the minimum of the distance squared, which is 0 if the 2 points are equal. On the other hand, if beta goes to infinity, what is happening here is that I am ignoring this cost for going too far, and therefore I will be certainly projected very much out of my domain. So there is some beta in the middle, which does the job of compromising between these two different requirements, believing your local gradient and not believing too much. So the important thing here, the important message is that if we solve this optimization problem over the next pi prime, we are actually doing gradient ascent. Why is that? Well, because it's you realize that the term in brackets here, this one, is a quadratic object in pi prime. This is quadratic. And since it's quadratic in pi prime, because this first term here is linear, and this one is just quadratic, then we can do the optimizations in a very straightforward manner. So we just have to take the derivative of what is inside the bracket with respect to pi prime. Okay, so if we do that, so let's introduce an object which we can call the Lagrangian, which is just this b grad g pi times pi prime minus pi minus 1/2. So this product, this dot product here and this norm here is just I sum over all possible A and S. So explicitly, I can write this down if you find it clearer. This dg d pi s pi prime minus pi. In our case, right? But of course, this is valid for much larger. This is one possibility. There are many of those, right? So this is p prime as minus pi as everything squared. Okay. So if notice that I have to add something here because I want to optimize, but pi prime must be a probability. So I have to enforce the fact that pi prime, the sum over pi prime of AS must be equal to 1. So what I do is actually I add to my Lagrangian a multiplier which enforces this condition. This is the Lagrange multiplier that imposes the normalization of probabilities. And then I can take the derivatives of my Lagrange function in order to find the maximum. And how does it look like? Sorry, this is with respect to pi prime. How does that look like? Well, it's very simple because this is a linear. The first term here is linear. So the derivative gives me beta grad g pi. Then this other second term here is quadratic, which gives me minus pi prime minus pi. And then I have the Lagrangian multiplier, which enforces the normalization. Okay, but let's ignore this for a moment. The most important thing here is to, okay, I could put a lambda and then impose normalization. Okay, let's put it. Okay. Now this object here, the job that it's doing is, you realize this gives me pi prime equals to pi plus beta grad g pi. So this is the gradient ascent step. And what this object here does is it enforces normalization. So this is the projection. Okay, so I'm not going through the details. You could also implement via Lagrange multipliers the condition that the pi's must be, the pi primes must also be positive. Okay, I'm not doing that, but this is just to tell you that there is a deep connection between gradient ascent with projection and this optimization problem. Okay, so you can go from one description to another. Following the gradient also means making some compromise between the gradient itself and some notion of a distance. So this, why do we care about this connection? Because this suggests different ways by which we can follow the gradient. And the basic idea is that we want to replace this object with some other notion of distance. Because this notion of Euclidean distance for probabilities is probably not the best one. So this is also a very general idea that when you have to deal with complex spaces, not necessarily your Euclidean measure is the right one. So what is a better choice? So what we want to do is want to repeat this kind of argument, but now with a different distance. So we want to move in policy space according to this rule. So we want to find pi prime. My new policy pi prime is going to be the argmax over pi prime of the same thing, some beta, the gradient of g times pi prime minus pi. And now I'm going to penalize this with some other notion of distance between the two policies. So do you know of any reasonable definition of distance between probabilities that you have encountered so far? Is any one of you aware of? So if I have two probability distributions, what is a way of measuring how far they are from each other? Exactly, Kullback-Leibler divergence. Okay, so what we're going to do, we're going to repeat this argument by using Kullback-Leibler divergence. So if any one of you is not familiar with the notion of Kullback-Leibler divergence, this is something that you should fix because it's a very widespread notion in machine learning and probability and information theory. But I assume that the level of knowledge that you need to be able to control this kind of calculation and operations is sort of very, very basic. So you can find it on every manual. It's not very in deep. So now we're going to use KL divergence, but in a way that is tailored to our problem at hand. Okay. So what are we going to do? Because we don't have a single policy, we don't have a single probability distribution. We have a collection of probability distributions. we have a probability distribution for every state. So we have to combine sort of all these policies to make a global distance between two policies rather than between two probability distributions. So the way I'm going to define this distance between two policies is just as the sum over all states weighted with my occupation distribution. This is the same eta that we've been using before for the gradient. And then we have my Kullback-Leibler divergence between the policy P prime in S and the policy pi in S. Okay, so it's a linear combination of Kullback-Leibler divergences. But since these objects etas are positive, it behaves pretty much as an ordinary Kullback-Leibler divergence. So it's a proper notion of distance. It's not strictly speaking a distance because, you know, it's not symmetric. It doesn't obey all the properties to being defined properly as a distance, but it's a divergence. So it's a measure of separation between two policies. So now let's try and do the same thing that we did before, now with this object. Clearly, this quantity here now is not anymore quadratic. It's more complicated. But the bottom line is that will be that if we use the Kullback-Leibler divergence, we are actually able to do this maximization exactly. Okay, so let's see how it works. Remember always that we have to impose the conditions on the normalization of pi prime and the positivity. Okay, so in this case as well, there will be a Lagrangian, which we can write as B grad G dot pi prime minus pi. And then we have minus the distance. And then we have plus sorry, I have to put this inside. Not that. I have to impose normalization for each. This is a set of Lagrange multipliers. I also multiply them by eta s for a reason that will be clear in a second. And then I have to impose the condition that my policies are normalized to 1. Okay? So these are Lagrange multipliers. And these are the constraints. Again, here I should also take care of the condition of positivity. But as we will see in a second, in this case, it will turn out that we can enforce them automatically. Okay, it's a property, it's a good property of the Kullback-Leibler divergences. So let's take the derivatives. Okay, we're going to take the derivative of my Lagrange multiplier with respect to policy pi prime AS. And now we're going to use the explicit expression of the gradient here. So let's go one step at a time. So we have beta, then we have dg in d pi. This is computed in pi. Okay, so this is when I take the derivative with respect to pi prime of this term, this is what I get. Then I have to take the derivative with respect to pi as of this d pi pi. So let's write it d. And then if I take the other derivative, I get minus lambda s eta s. And all of this will have to be 0. Okay, now it's time to replace these quantities with the ones that I've calculated. So this object here, I know it. So this is going to be beta, eta of s, q of SA. This comes from the policy gradient theorem. So what about the derivative with respect to pi as? Okay, let's look at this. Okay, so first thing we are deriving with respect to the index s in the policy. Okay, so the sum over s goes away, and we are left with minus eta of s. And then we have to take d pi as of the Kullback-Leibler divergence between pi prime, es, and pi. Okay, I'm going very slowly. It's just when I take the derivative, I kill all the terms except the ones which have the s, and then I have to take the derivative of the Kullback-Leibler, and then I have minus lambda s, everything. Okay, so at this step, you see, I have artfully introduced all these eta s, which are positive, so that I can get rid of them here. Sorry, not this one. Now, last step, I have to take the derivative of the Kullback-Leibler divergence. So let's remember that this is d in d pi as. So let's write the Kullback-Leibler divergence explicitly. So what is it? It's the sum over all possible actions. Let's write a prime of what? Of pi prime a prime s logarithm of pi prime a prime s divided by a prime s.
I think the derivative is with respect to pi prime.
Derivative is with respect to pi prime. Yes, thank you. Also here. Thank you very much. So this is the term that we are considering here. So now this is easy because I have just to derive this object, and it's a straightforward calculation. You just get logarithm of pi prime a s divided by pi a s plus 1. And then I can plug this back in. This I can plug back in here. And what do I find? Well, I find beta q sa minus log pi prime as plus 1 minus lambda s equal to 0. And here is where the nice properties of the Kullback-Leibler divergence become fully can be fully appreciated, because this allows me to write down explicitly pi prime as a function of pi as e to the beta QSA. And then I can normalize. That's where my Lagrangian multiplier comes into the game. I can normalize this. So before we discuss this result, so let's make a few remarks. So first remark is that if pi is positive, as it should be, then also pi prime is positive. And pi prime is normalized. So in this case, you see that we don't need to make any projection. If you make one step, if we start with a policy which is within the admissible range, the next one will still be in. There's no risk of going outside the domain. This is a property of the Kullback-Leibler divergence. First remark. So to recapitulate, remember what we've been doing here is that we've been doing a sort of gradient ascent, but now with a different notion of distance between points in our space. That is distance between policies. That's what we've been doing here. So as a result, if we start from a policy, we get to a new policy, which is obtained by multiplying each entry of my policy by exponential of beta of the Q function of that policy. Clearly, this skews the probability distribution towards the entries which have a larger Q. So where my matrix Q is larger, there will be more probability. So this makes sense. I have a policy, I construct an estimate of what this policy is worth, and then I get to a new policy which has larger entries in the items, in the actions that give the most. So let's have a look at what is happening in the extreme cases. So clearly, if beta equals 0, then pi prime is going to be equal to pi. That was to be expected, because what does beta mean? Well, if you have a look at the optimization problem here, when beta is 0, it means that you don't want to, you pay a cost for moving away from the point without getting no compensation for that, because beta is 0. On the contrary, now when beta goes to infinity, something interesting happens here, because now you don't get outside the domain, because you're always inside your policy space. So what happens when beta goes to infinity? When beta goes to infinity, your new policy pi prime, look, if beta becomes very large, here there is many exponentials that are competing with each other, but only the one which has the largest entry will win. So this object here on the left-hand side becomes the argmax over A of Q pi SA. In fact, you can think of this function here as a softmax, as a so-called softmax. It's a way to take the maximum but soften it. Okay. So, but this is the greedy strategy. So in this limit, beta going to infinity, our gradient ascent with Kullback-Leibler divergence becomes the policy iteration. So in a sense, we have forgotten the request that we have to stay close to our initial point, because the weight on the distance is getting very small, because the importance of the distance with respect to the gradient is 1 over beta. So we forget about this notion of distance, and then we go full throttle to optimize over the gradient. And we recover the original policy iteration that we have been discussing at the beginning of the lecture today. Okay? And of course, if you tune properly your beta, you will be making the right steps in the proper direction. And this is a very effective algorithm for policy improvement, because you don't visit all the corners. So in a sense, let's make a graphical summary of what is happening here. So this is our policy space. Suppose we start with a pi. Then if we, this is my gradient of G. Then if beta is infinity, I just go the corner here, and then corner here, and then the corner here. So this is what happens when beta is infinity. When beta is 0, I don't move. And for intermediate betas, I take a step somewhere in this direction, and then another in this direction, and then this length, the length of these steps is variable, but I'm guaranteed that I will never go outside my policy space. So this case that I discussed here, so this algorithm here, okay, because you clearly see that you can turn this into an algorithm. Let's write it explicitly. This algorithm has a name, and it's called mirror ascent. Why it's mirror, it's a complicated issue, but this is the name that comes in optimization theory. Works as follows. So initialization, your policy pi 0 as usual. And then you have to iterate in a loop. From your policy pi k, compute your Q function, qk, as we did several times so far today. And then get your new pi prime, sorry, not pi prime, but pi k plus 1 equals to pi k exponential of beta qk normalized. Okay, so what I mean here is AS, SA, SA prime, SA, A prime. Okay? And this goes on until, as always, there is, for instance, you can termination. In this case, might be, for instance, when your distance between the new policy and the previous one is smaller than some epsilon. So this means that your steps are becoming smaller and smaller because you're close to the optimum. Or there might be other ways, or you can also use your Q function as a terminator, whatever. Okay. So this is actually an instantiation of a much broader class of algorithms, which are this online mirror descent, online are called sort of online. I forgot. Online mirror ascent or mirror descent, if you want to minimize, which are of enormous importance in convex optimization theory, and find an application in this context. Okay. I think I said more or less everything I wanted to say about this algorithms in policy space. So we did not have time to discuss the problems and answers that arise when you mix these algorithms, either value iteration or policy iteration, with the function approximation. but this will be the subject of the next lecture. Not tomorrow, because tomorrow we are going to have a tutorial on value iteration with practical applications. But let me just make a short graphical summary of what we have achieved so far. So we have two possible approaches, basically, for solving an MDP. By value iteration. Okay, so graphically, this means that you're working in the space of value functions. Okay, so this is abstractly the space of value functions. This is the value for state 1, value for state 2, value for state 3, and then there may be other many axes that that don't make any sense on a picture, but something like this. And then you start from a certain V node, and you use the Bellman operator to send you to a V1, and this will send you to another V2. And all this process eventually converges to V star, which is the solution of the Bellman equation, BV star equals V star. Tomorrow, we will see examples of this procedure of dynamic programming. Second possibility is policy search. Okay, now the thing happens simultaneously both in the space of values and in the space of policies. Okay, so this is symbolic for both. Okay, don't take this literally. So what is the idea here? The idea is that you start with the policy pi 0, and you use this to compute a value v0. This new value allows you to compute a Q0 function, which somehow by either algorithm, for instance, by this algorithm here, your new Q will send you to a new pi 1 here. And this pi 1 will send you to a new V1. And this V1 will compute the Q1, which will send you to pi 2, and so on and so forth. And this going back and forth between the policy space and value space will eventually lead you down here at your optimal policy pi star, which will correspond to an optimal value v star. Okay, so you go back and forth like in a tennis table game. Eventually, this procedure stabilizes between the optimal value on the left and the optimal policy on the right. Both these kind of problems and architectures will be very important when we deal with model-free problems. That is, we will be able to use the same kind of ideas even if we don't know what the transition probabilities and rewards are. So that's why I'm insisting a lot on this. Okay? And I think that's a good point to stop. Any question? I suppose you have to digest all this.
Yes. Can
Yes,
I
please.
see what you wrote just before? The first example. Yes, perfect. Just 1 second.
Sure. Again, if you want to play around with these two approaches with a two-state two-action model, then you can clearly visualize everything, because the value space is two-dimensional, the policy space is two-dimensional, so you can really see these points moving around, and it gives I think a very, very neat interpretation. Of course, this kind of exercises could be the basis for your final for your evaluation as a sort of exam. Okay, this is just a suggestion. There will be many more things to come. So this is one possible entry for your final assignment. Okay. There are no further questions. I'll stop sharing and stop recording.